Hi, I'm going to give you an example of a calorimetry problem. And it's a fairly stereotypical one. We're going to take ice, throw it into water, and make some measurements in order to make a calculation. So the ice, let's say that we start with 50 grams of ice. So mass of the ice is 0.050 kilograms. Let's go ahead and switch to SI units right away. And the initial temperature of the ice, so temperature initial for the ice is equal to minus 10 degrees Celsius. Now technically that's not SI. We could convert it to Kelvin if we wanted, but it's not necessary because all the formulas here deal with temperature change, not absolute temperature, so we'll be fine with Celsius. We'll leave it alone. Okay, and then we have the water, the warm water that we throw it into has an unknown mass. So that's going to be our variable of interest. We're going to try to calculate that using other measurements. And the initial temperature for the water is 30 degrees Celsius. And we mix these together and find that they come to in an isolated insulated container, and we find that they come to a temperature of 20 degrees. So T final, once they're well mixed, is 20 degrees Celsius. Okay, so we also have some empirical values. We know, like specific heat capacities, latent heat diffusion, and things like that you can look up in a table. So how are we going to figure this out? So a lot of sources will use sort of a piecemeal method where they'll make all these separate little calculations and then eventually get to what you're trying to do. But it's very easy to go wrong that way. What I usually do for calorimetry problems is start by thinking about the fact that it's isolated. So most of these problems we're dealing with an isolated system. The heat flows out of the water and into the ice, but whatever the water loses, the ice gains, and so the total is zero. So let's write down a very concise statement. Total Q equals zero. Okay, that's kind of your starting point for most calorimetry problems. And then you think about, well, who's involved here? So we have the ice, we have the water. So Q for the ice plus Q for the liquid water equals zero. Okay, so far pretty simple equation there, but it's going to get messy real fast. And so the reason is that the heat for the ice actually is going to have three components to it. So we have solid water at minus 10 degrees. It's going to be brought up to zero. That's one process. Then it needs to melt, second process, and then it needs to be brought up to 20 degrees. So it undergoes three processes, so Q involves three different things. For the water, all it does is drop from 30 down to 20. There's no phase change, so it's pretty simple. But I'm going to actually have four terms in my calculation of heat. So let's go ahead and start writing that down in all its glory. It's going to be a big, long, ugly equation, but we'll make it work. So first thing is temperature change from minus 10 to 0. But we'll leave it as variables. So mass of the ice, C for ice, okay, so that we wouldn't want to use C for liquid water. We use C for solid water, times its temperature change. We don't write delta T. We split it up into final minus initial. But we don't use this number right here. We use final for this particular process, which is going from minus 10 up to 0. Okay, so I'm going to write this down as temperature in the middle for the ice, which is 0 degrees Celsius. So it goes from minus 10 to 0 up to 20. So really, the ice really has three distinct temperatures that we need to be thinking about. So its final for this process would be temperature of the middle for the ice minus temperature initial for the ice. Okay, so that hopefully familiar formula, MC delta T, that's what we'd use for the going from minus 10 to 0. Okay, at that point, any energy that goes into the ice doesn't make the molecules move faster. It changes the bonds between the molecules, and that process we keep track of with the latent heat of fusion. So energy can be calculated this way: Q equals mass of ice times latent heat of fusion. Okay. All right, so now we have it melted, but it still has to be brought up to 20 degrees Celsius. So one more MC delta T would be mass of ice. And now we use C for liquid water. And delta T, and we don't write delta T because that could be confusing. We do final temperature minus the intermediate temperature. So T final minus temperature in the middle for the ice. Okay, so that's all that stuff is Q for the ice. Okay, we're not done. So we have to write out this one. Q for the water is a little simpler. It just lowers its temperature. So mass of water, C for water, times temperature change for the water. So final temperature minus initial temperature for the water, and equals 0. Okay, so there it is in all its glory. That's conservation of energy for an isolated system where the two subsystems are exchanging energy in the form of heat, and they're including one phase change. Okay, so all that stuff is known. So we have, except for mass of the water. So we have some numbers here that we know. We know some temperatures. We know one of the masses, and these specific heat capacities, heat of fusion, are empirical values we can look up in a table. So this big mess here is one equation, one unknown. It is solvable for the mass of the water. You can do that. Okay, so you might try that yourself. If you want to pause the video and do the algebra by yourself, or you can just watch me do it if you're not that interested in doing the algebra. So we end up with that the mass of the water, okay, I'm going to skip steps here, but basically we take all this stuff, the Q for the ice, subtract it, okay, put it over to the other side. So minus, and I'll put it in a big bracket, so just copying symbols. Oops, I messed up in copying the symbols. That would be C for ice. Oops, ran out of space there, but that's T, temperature in the middle. Okay, and then we divide by this stuff right here. So C for the water, temperature change for the water. Okay, so it looks like we might end up with a negative sign, but no worries. We'll get a positive mass. We'll get antimatter here because the temperature change for the ice is going to give us a negative number. Okay, so mass of the water would be equal to, let's throw in the numbers. So mass of the ice, 0.05 times C for ice, which is 20. Should have that memorized. 2093. Times temperature middle, 0 minus temperature initial, negative 10, okay, plus mass of the ice, which is 0.05, times heat of fusion, 3.34 times 10 to the 5th, plus, sorry, I'm running out of space here, 0.05 times heat of fusion for water, which is 4190. And then final temperature of 20 minus the intermediate temperature of 0, all over specific heat capacity of water, 4190 times the temperature change for the water, which was 20 minus 30. Okay, so you take all that mess, throw that into your calculator, and throw it into, and see what it gets. Get 0.573 kilograms. And that, I think that's fairly intuitive. We have about 10 times the mass of water that we did ice. We threw in, a little bit of ice, and we lowered the temperature by 10 degrees. I think that would be concurrent with our everyday experience. Yeah, so, I mean, why, if we knew the mass of the ice, why don't we just throw the water on the scale? I don't know. But anyway, you can calculate mass indirectly using calorimetry. Okay, so hopefully that example is useful. But just remember, when you're doing these calorimetry problems, this is your starting point, and then you think about the specifics of the physical situation with MC delta T or M times L for the phase changes. Okay, so thanks for watching. I'll see you next time.